Why are the first and second principal components of data at right angles to each other? Autoencoders are neural networks which serve to find compact representations of underlying data. Autoencoders work by trying to reconstruct the input at its output. This might sound trivial, but autoencoders are often constrained in some way. There are several ways to constrain an autoencoder neural network. You can limit the size of the internal representation so that the autoencoder is forced to learn the most important latent factors which drive the data. You can also add noise to the input and force the autoencoder to reconstruct the original from the noisy input. All of these force the autoencoder to identify the important factors or the latent factors which drive the underlying data. And finding these patterns in a data set is basically principal components analysis. Let's understand what principal components analysis is and how it helps in dimensionality reduction of your data. We'll start off by considering data in one dimension. Unidimensional data can be plotted on a single number line. It has just one attribute, a number that's associated with it. Unidimensional data is kind of boring. It will not hold very many insights by itself. Data is much more interesting when you view it in relation to some other bits of data which are related to the first. That is data in two dimensions. Every point here is represented by two numbers or two coordinates. Let's look at some data here and answer some questions. You have this 2D data or two dimensional data as you see on screen. Do we really need two dimensions to express all the information that's present in this data set? As in the case of most real world scenarios, the answer to this question is that it depends. Now, if you were to choose the axes or dimensions of this data poorly, then we do indeed need two dimensions. If you were to basically represent the data on the axis that we've drawn on screen, all of the data would boil down to a single point and we've lost all the information in the underlying data. In this case, we absolutely do require two dimensions to represent this data. But what if we move this entire data set to the y axis? We projected it on the y axis rather than the x axis. In this case, we've chosen our dimensions and axes well, then one dimension is sufficient to represent this data. All the different points and how they're spread out has been completely represented by moving this data to the y axis. And this example that we just saw should underscore to you the importance of choosing the right axis to represent the data. If we make a good choice of axis, then we don't require as many dimensions to represent the same data set. With this in mind, let's move on to the intuition behind principal components analysis. We have a number of data points here, all the x's that you see on screen. Our objective is to find the best directions or the best axes to represent this data. You can start off by drawing some line in some direction and projecting all of the data points onto that line. For example, we've drawn a horizontal line here, and all of the data points we've projected or moved onto that line. How good this projection is and how good this particular axis is to represent the data that you see on screen is determined by the distances between the points on this line. The greater the distances between these projections, the better the direction of the line that you've chosen. You can intuitively tell that if the distances between these points are larger, then a lot of the information contained in the original data points have been captured by the projected points on this line. Contrast this projection with the example that we saw earlier, where all of the points were in a single line and we projected it on to the x axis. This projection, where the distances are minimized, is a bad one. We've actually lost a significant portion of the information contained in these data points. All of these data points have been reduced to a single point. The second example that we saw earlier, where we projected these points onto the y axis, is when the distances are maximized. Information contained within these points is preserved. This is a good projection. This just reinforces the point that when you choose the axes to represent data, you want to make sure that the distances between projections are maximized or as much information as possible is captured. Let's use from technical terms for these. The distances between points when projected in a certain direction is called the variance. The direction along which this variance is maximized is called the first principal component of the original data. Remember, when we started off, we just had the bunch of points on screen. We chose this direction. We pick the direction so that the variance of these points is maximized when they are projected in this direction. We've chosen the first principal component. Our example data is in two-dimensional space, and we've chosen just a single axis on which we've projected this data. All the information of the original data points haven't been captured. Most of it has been, and that's in the first principal component. Now, in order to capture the remaining information of within these data points, you need one more axis. To choose this second axis, you need to find the next best direction. The points, when projected in this direction, should capture the second largest variance or distance between the points. By definition, to capture as much information from the remaining direction as possible, this next best direction must be at right angles to the first principal component. This is the second principal component. The first and the second principal components are always at right angles to each other. This is because directions at right angles are the ones that express the most variation with the fewest number of directions. For data that is expressed in two dimensions, these two principal components capture all of the underlying information in the data. If these two principal components weren't at right angles to each other, some information would still be lost in spite of having two axes or two directions for to represent the data. By definition, the first principal component is chosen such that it captures the highest variance in the input data. The second principal component will clearly have smaller variances as compared with the first. The principal components are named the first principal component, the second principal component, and so on in the descending order of the amount of information captured by each of these components. The number of principal components that you require to express all the information in your underlying data is equal to the number of dimensions in your original data. You have as many principal components as there are dimensions in the original data. If the original data was 3D data, then you have three principal components. For n dimensional data, you have n principal components. Let's say these blue dots on screen form your original data, and they're originally expressed along the x and y axis that you can see in black on screen. You'll redraw principal components PCA1 and PCA2, which captures the maximum and then the second most variance in the underlying data. You'll then turn or reorient the entire data set around so that they're expressed in terms of these new axes. And this reorientation of your data to be expressed in terms of its principal components is principal components analysis. Now, the interesting thing about these principal components is that the first principal component captures the maximum amount of information possible about the underlying data set. The second principal component has a little less information. The third principal component has even less information, and so on. Now, after re expressing your data in this manner, if you find that the variance along the second principal component is small enough, it's insignificant, then we can just ignore it and use just one dimension to represent the data. If the first dimension has basically captured most of the important information in the underlying data, we can ignore the second dimension. And this is how principal components analysis allows us to express data in fewer dimensions. This representation is more compact and captures the essence of the underlying data. And this is how PCA is used for dimensionality reduction. You use fewer attributes or fewer axes to represent the same information. And principal components analysis allows you to pick the most important attributes, the attributes which capture the most information about the underlying data set. Let's understand dimensionality reduction in terms of matrices. These matrices represent our input data set. The matrix that you can see on screen has a total of k columns. The total number of rows is equal to n. That means there are n data points that are represented in this matrix, and each point has k attributes or k dimensions. Now you can feed this data into an algorithm which performs the principal components analysis. This will generate principal components, and you can represent this data in fewer dimensions. You can represent the essence of this data with fewer columns or fewer attributes per data points. Here, after PCA, we've expressed our data in two columns. Our input data had k columns and n rows, that is, n data points expressed using k attributes, and all of these attributes are probably highly correlated with each other. We pass it into our PCA algorithm, and the same data can now be expressed in terms of principal components. Now, the feature of these principal components is the fact that each of these attributes, they are still k axes, because if you have k dimensions in the original data, there are k principal components which can be generated. The fact is, though, that each of these principal components are completely uncorrelated with each other. So you go from correlated data to uncorrelated data, even if you have the same number of axes. Once you have expressed the data using principal components, you can capture most of the information in the underlying data using fewer dimensions. This is dimensionality reduction. If you were to choose, say, the first two principal components to represent this data, these components explain the vast majority of the total variance in the original data. Remember, we picked those components based on the direction which captured the highest variance, second highest variance, and so on. Principal components analysis involves expressing the data in terms of its principal components or variables that are uncorrelated with each other. The original data and the principal components have the same dimensionality, the same number of columns. It's only once you have these principal components that you can choose to represent the same data with fewer dimensions. Let's say you choose the first two principal components. Now, you can always reconstruct the original data from the principal components that you have. You have the principal components, you simply multiply it using a weight vector that is generated during the PCA process. This weight vector is a k by k matrix where k is the number of axes in the original data and is a measure of the contribution of each of the principal components. Multiplying the principal components by the weight vectors will give you the original data back. This allows you to reconstruct the original data. Principal components are projections of the data on axes which are drawn in such a way so as to capture the maximum variance in the underlying data. The first principal component captures the largest variance in the data. The second principal component, in order to capture the second largest variance, has to be perpendicular to the first. The principal components are perpendicular to each other to capture the most variance with the fewest dimensions.